walk through using ggplot2. ggplot2 is plotting a set of plotting functions in R. So this is an intro to ggplot2. Whenever I do anything, I need to know where I am, so I check where my current working directory is, and I use this function get working directory, and I run that. I run line 5, and I see that I'm actually using Google Drive to store all my work. I have a folder called courses. One of my courses is 209W, and inside that I have a folder called RWork, so that's where I am. And if we look in the bottom corner, bottom right hand corner, you can see the files I have in that directory. So next I'm going to load ggplot2. ggplot2 is part of the tidyverse, so we could load all of the packages in the tidyverse, but I'm going to choose not to. I'm just going to load ggplot2. I could do either one. So I put the cursor there, and I hit command return on my Mac, and you could do something similar on your Windows machine. And there we can see that I have loaded ggplot2. Next I'm going to make up some data. I'm going to make up some data that I'm going to call X and Y, because I'm going to plot these data on an X and Y scatter plot. So my first data are actually random uniform numbers, and I'm going to have 10 numbers, and the minimum of these random numbers could be as low as 0, and the maximum could be as high as 10. So I make those numbers. Now I'm going to make Y that is equal to 2 times X, whatever X is, and I'm going to add 5 to that. So I've got X here, and I'm going to say that Y is going to be equal to, say, a slope mx plus b. So I've got this one. You'll see that this becomes a slope as a function of x plus an intercept of 5. So I'll run that. And then I'm going to add a little bit of noise to that, just random noise, to make it kind of an imperfect relationship or a noisy relationship. And R has another function to generate random normal variables that are randomly distributed. And this will generate random normal numbers with a mean of 0 and a standard deviation of 1. That's not important. We're just going to add some noise to it, and we're going to call it Y2. So we'll run that. Now I'm going to stick it all in a data frame, and by now you may be thinking of data frame. When you think data frame, think spreadsheet. It's an array of variables in an organized form. And I'm going to call X uppercase X to distinguish it, and I'll call Y uppercase Y, and I'll call Y2 uppercase Y2. And I'll put all those in a data frame, and now I can just look at those. I'll run line 17, and there they are. I got my X, I got my Y, I got my Y2. And you might notice that as X gets bigger, Y gets bigger. Now let's plot these in a scatter plot. GG2 has a common structure to all of its plots, and we'll walk through what that is. To use these plotting functions, we start with ggplot, just ggplot, not ggplot2, which is the name of the package. We say ggplot parentheses, ggplot parentheses, and then data equals, and then name the data frame. And my data frame is called D. So I say the data are D, comma, and then I specify the aesthetics. I don't know why they call them the aesthetics, but they do. So these are the aesthetics, in this case X and Y. So what's going on the x-axis, this lowercase x stands for whatever's on the x-axis. I'm going to put X on the x-axis, and on the y-axis I'll put my y data. So there I've specified the data frame and and the variables in the data frame that I want to use. And I close these parentheses. So they all match. And then I add a plus sign because I'm not finished. I'm telling R that I'm going to do a little bit more. And the next thing I'm going to do is I'm going to use a geometric representation of these as points. That's what geom_point is. It's a geometric representation in 2 dimensions of points. And I just have open parentheses, close parentheses. I run those, and voila, and we can see in the bottom right-hand corner here, we've got a plot of x and y, or y as a function of x, and we can see those points line up as a straight line, because for every unit increase in x, we get twice that in y, because that's how we defined y. And notice that the y-intercept is 5, because we added 5 to all these numbers. And those line up on a perfectly straight line. Now let's do the same thing, except we're going to plot the noisy version of y, or y2. So again, we've got ggplot2. The data, we tell ggplot what the data are, what the data set is. We tell ggplot2 which variables we're using. We're using x, and we're using, on the y-axis, we'll put y2 now. And again, we add the plus because we're not finished. And then we're going to make a scatter plot with points. So we add geom_point. And I run those lines, and what do I get? And now I can see the sort of noisy, slightly noisy relationship between x and y, because I added that noise to make that thing called y2. Now what if we'd like a line, to try to fit a line through those? Well, ggplot2 has several functions to do this, and one of them, the main one, is called geom_smooth. We're going to plot a smooth line through those points. And so we're just going to add that. So we say ggplot, tell it what the data are, the aesthetics, or the x and y are x equals x, and y equals y2. We're going to add the points. We're still not finished. We're going to add geom_smooth. We're going to put a smooth line through there. I run those, and I get a smooth line. And that blue line, you've done this before. We add that smooth line, and we have uncertainty around the estimate of that line. And we can take that estimate away, or we'll leave it on for now. Often, we tend to plot straight lines through things. And so if we want to do that, we can specify that the method of putting a smooth line in there is a linear model based on ordinary least squares regression. And so we say method lm, and so the method equals quote lm unquote, and then close parentheses. We run this, and now we see a fitted straight line. And that's how we plot scatter plots, where x is a continuous variable and y is a continuous variable. All right? Now let's move on to categories and box and whisker plots. Often we have categories of something. We've got maybe different types of plants. Maybe we have lianas and we have trees, or we have cats and we have dogs, or we have whatever category you want. Let's use some, and we want to plot characteristics of those. Let's use a built-in data set, which is mileage data for different kinds of cars. This is built into data, and it's called MPG. And so if we say names MPG, we'll get the names of the variables in that data set. And when I do that, I see that the manufacturer, we will be told the manufacturer, the model, the displacement, which is essentially the size of the engine, the year, the number of cylinders, what transmission type it is, whether it's manual or automatic. And then it's got city mileage, it's got highway mileage, and other stuff that I forget. So those are our data. So we'll do the same thing. We'll tell ggplot we'll say use this data set MPG. We'll say that the X and Y variables is the class, what type of car it is, like whether it's a pickup truck or a two-seater sports car or something. And the Y variable is highway mileage. And now we're going to draw a box and whisker plot. And we'll describe what that is. We'll describe what that is when we display it. So now we see in the bottom right hand corner, we see the type of car on the x-axis, and you'll notice these are categories now. This isn't a continuous numeric variable. And on the y-axis, we have highway mileage. And we have a series of box and whisker plots. Box and whisker plots are a great way to present data when you want to show your data, when you want to show the variation plus central tendencies. Let's go to this compact class of car. So these are small cars, and the highway mileage averages about 27 miles per gallon. This heavy black line is the median, so 50% of the points, 50% of the data lie above this line and 50% lie below this line. That's the median, not the mean. The upper bound of this box and the lower bound of this box represent the lower 25th, what they call a quantile. It's like the percentile. And this upper bound of the box represents the upper 75th percentile or quantile. So 50% of the data lie inside that box. So we can really see, okay, half the cars are right about here, but some are smaller and some are bigger. These tails are, you can define them in various ways, but they extend out to the last point, if the last point is within 1.5 times this distance, or the last point, whichever's closer. And then if there are points beyond that extreme, then they are considered, quote, outliers, and they're an individual point is plotted for them. So some of these groups have outliers and some don't. But the point is, we've got some category that we want to these categories that we want to compare, and we've got a continuous variable that we're interested in. So when you get to the liana data or other data, you may have different kinds of, say, trees versus lianas, one species versus another, morning versus evening. When you've got categories, you can present the data in terms of box and whisker plots. These box and whisker plots have one particular feature that's kind of interesting. And I'm also going to show you something else that's interesting. You'll notice that up until this point, we've been saying, we've been defining the data set and what the x variable is and what the y variable is. And so you can build these plots sort of stepwise. And so what we're going to do, what the next step does, is define that part of the model, that part of the graphical display, and we'll stick it in an object called P. So I run that, and now I'm going to make a plot in which I'm going to take that P, because I've defined P as this. So now to P, I will add my box plot. And so I can just say P plus geom box plot, and I get the same box plot again. All right, so we can build these things stepwise. Another feature of box plots is we can add a notch. And this notch actually has some statistical value. It defines a confidence limit on this notch. You can see this little notch inside these boxes. This notch actually defines a 95% confidence interval according to one method. It uses a method to define the 95% confidence interval on the median, so we have some level of confidence about whether or not two medians differ from one another. So we can say, all right, these medians, they look similar, and indeed their confidence intervals completely overlap. And so that can be a convenient thing. The very last thing I'm going to show you is what's referred to as faceting. Let me delete this. And perhaps we want to consider one of these things at a time. Imagine that we are interested in now in the displacement, the engine size, and the city mileage. And we'll make a graph of that, and we can say P. What is P? This is the relationship between engine size on the x-axis and the city mileage on the y-axis. And you can see the bigger the engine, the worse the city mileage. No shock there. Well, we might also be interested in how that might vary between the type of drivetrain it has or between the number of cylinders it has. So we can say, what if we wanted to break up the data and compare it among different types of things? And to do that, we use what ggplot calls faceting. Like a fine diamond, we expose different sides of the data. And to do that, we use one thing we can use is a function called facet grid, facet_grid parentheses. And for this, we define which plots we want in rows and columns. So here's a variable. I think it's what type of drivetrain it has. We'll find out in a moment. We use this tilde, this squiggly line, which you'll find in the upper left-hand corner of your keyboard, and this dot to represent that is just a placeholder. So when we do this, when we plot this, you'll notice that when we put the whatever type of drivetrain it here is, we've got four-wheel drive, front-wheel drive, and rear-wheel drive. That's what that is. What kind of drivetrain? Four-wheel drive, rear-wheel drive, or front-wheel drive. We put those in columns, so we stack up these plots in columns. Alternatively, we could we could arrange these plots across the page in one row and actually array these in different columns. You can think of this current plot as the four-wheel drive are in the first row, the front-wheel drive are in the second row, and the rear-wheel drive are in the third row. Now we can, if we flip these around and we put the placeholder, the dot, the period first, and then the tilde, and then the name of the variable, the name of the category, now we can see that the number of cylinders, each number of cylinder is in a separate column. So the four-cylinder engines are in the first column, the five-cylinder engines, which is rare, in the second column. 6 cylinders, 8 cylinders, they're arrayed in columns. We can even do both, and that's what this last thing is. And so we look at all combinations of the type of drivetrain and the number of cylinders, and for each combination we're examining the relationship between engine size or displacement and the city mileage.